All right, let's dive into one of the most powerful ideas in all of statistics, hypothesis testing. Now, I know that sounds kind of intimidating, but trust me, this is the main tool that pretty much everyone, from scientists to big companies, uses to make smart decisions with data. And to really get it, all we need to do is learn its language. So let's ask the big question. How do you actually use data to test a claim? To figure out if a new drug actually works, or if that big marketing campaign was worth the money. It might seem super complicated, but the logic behind it is something you're already totally familiar with. In fact, it's almost a perfect mirror of a courtroom trial. So for the next few minutes, I want you to forget we're talking about stats. Instead, imagine we're all stepping into a courtroom. A huge claim has been made, and we're officially putting it on trial. But our evidence? It isn't going to be fingerprints or witnesses. It's going to be something way more powerful, data. Now, every trial needs a defendant, right? And in our statistical courtroom, that defendant has a very specific, kind of nerdy name. So let's meet the key players in this whole drama. You see, every single test has two competing stories. On one side, we've got the null hypothesis, or H-naught. This is our defendant. It represents the status quo, the business as usual idea, the claim that nothing has changed, that there's no effect. And on the other side, that's the alternative hypothesis, or H1. This is the prosecutor's big claim, the new, exciting idea that we're hoping our data can prove. And this right here is probably the single most important rule of the entire game. Just like in a real court, our null hypothesis, our defendant, is presumed innocent. We have to assume it's true right from the start. We need absolutely overwhelming evidence from our data to challenge that and, convict it. Okay, so a prosecutor can't just walk into court and vaguely say, hey, I think something's up. No way. They have to be specific about the charge. And it's the same thing in statistics. We have to define the exact nature of our claim. And there are basically three ways we can frame this charge. A two-tailed test is like asking, hey, is this value just different than what we thought? Could be higher, could be lower, we don't care. A left-tailed test is more specific. Is the value actually less than we expected? And you guessed it, a right-tailed test asks, is the value greater? That little symbol we choose sets the entire strategy for the rest of the trial. All right, let's jump to the most intense moment, delivering the verdict. We've looked at all the evidence, our data, and now we have to make a call. But just like in any real courtroom drama, there's always a risk that we might get it wrong. So if you look at this grid, you can see there are really only 4 ways this whole thing can play out. 2 of them are great. We made the right call. We either acquit an innocent defendant or we convict a guilty one. Perfect. But those other 2 boxes, well, those are the errors. And they have very specific names and, believe me, very serious consequences. First up, we have what's called a type 1 error. This is a big one. This is when we reject the null hypothesis, our defendant, even though it was actually true the whole time. In our courtroom analogy, this is the absolute worst case scenario. We've just convicted an innocent person. It's a false positive, a complete miscarriage of justice. And then you've got the flip side, a type 2 error. This is what happens when we fail to reject the null hypothesis, even though the prosecutor's claim was right all along. Back in the courtroom, this means a guilty person just walked out the door scot-free because we just didn't have quite enough evidence to make the charge stick. Okay, so the verdict is in. How do we actually announce it to the world? Well, the language we use here is incredibly important. It's not as simple as just saying guilty or not guilty. Statisticians are very precise with their words. And this, right here, is the #1 rule you have to burn into your brain. We never say we accept the null hypothesis. Ever. Why? Well, think about it. Just because a prosecutor couldn't find enough evidence to convict someone, does that prove they're innocent? Of course not. It just means they didn't meet that high burden of proof. So our language has to reflect that reality. If we do have enough evidence to reject the null, our official statement is, there is sufficient evidence to support the claim. But if we don't have enough evidence, we have to say, there is not sufficient evidence. Notice how we never say the claim is false. We just say we couldn't prove it with the evidence we had. It's a subtle difference, but it's a huge one. Now, I know this can all feel a bit abstract, maybe a little academic, but I promise you, this courtroom logic is being used every single day to make decisions that affect all of our lives. Let's open up a few real-world case files. Okay, think about testing a brand new drug. The null hypothesis, our innocent defendant, is that the drug does nothing. It's just a sugar pill. So a type 1 error here means an ineffective, maybe even harmful drug gets approved and sent to pharmacies. But a type 2 error? That means a potentially life-saving, effective medicine gets thrown in the trash. You can just feel how high the stakes are. Or let's say you're in a factory. The null hypothesis is that the latest batch of phones or cars is totally fine. A type 1 error, that costs the company money. They throw away perfectly good products. But a type 2 error, wow, that's a potential disaster. Defective products get shipped out to all of us, leading to huge recalls and a ruined reputation. And this is where our whole metaphor just comes full circle, because the legal system is a form of hypothesis testing. The null hypothesis is literally the defendant is innocent, which means a type 1 error is convicting an innocent person, and a type 2 error is letting a guilty person go free. Our entire justice system is built around one single idea, to make one of these errors almost impossible to commit. Which one do you think it is?
So, I'll leave you with this final thought to chew on. If you're the one testing a new life-saving drug, but it might have some risky side effects, which error is more dangerous? Approving a drug that doesn't actually work or throwing away one that does? The answer isn't simple, is it? And it shows exactly why understanding this language, the language of hypothesis testing, isn't just for statisticians. It's for anyone who has to make a really tough call in a really uncertain world.